All right, this is Honors Algebra 2 Pre-Calculus. We're doing 8.7 in Algebra 2. This is the first video in this section, and we are simplifying radical expressions. So for any real number a, the nth root of a to the n cancels out and gives you the absolute value of a if n is a positive even integer. Okay, so what we're saying here is if the root, right, so by n being a positive even integer, oh, my bad, sorry, by n being a positive even integer, what we're saying is we're talking about an even root. So it's worth mentioning that because even roots always have positive or zero outputs. They have non-negative outputs, which I say down here as well. If the nth root of a to the n equals a if n is an odd integer, because odd roots can have positive or negative values out. So as an example, if I asked you what the square root of -5 squared is, right? You can logic through this. If you were cleaning this up, you'd make this the square root of 25, and I ask you what the square root of 25 is, you would tell me it's 5, right? But if you wanted to use this sort of property that we have here to cancel, you could just skip to saying, oh, it has to be the positive version of -5, which is going to give me a 5. If you did the cube root of, let's say, -2 to the third, right? You could clean this up and make this a cube root of -8, which is totally going to give you a -2. Or you could recognize that the cube root and the cube just cancel to give you a -2, right? Either way, you get a -2. The trick is that you can't have negative outputs from even roots. All right, so I'm going to go ahead and clean some stuff up a little bit. So we're going to fully simplify each radical. Now, a trick with variables is that variables can vary. So because of that, I have to put an absolute value. So I know that when I pull the 49 out. So let's go ahead and start by splitting this a into some stuff that's perfect squares, right? So what I'm going to do is I'm going to split the stuff in a into perfect squares. 49 is a perfect square. X squared is a perfect square. Y to the fourth is a perfect square. Z to the sixth is a perfect square. But you know who doesn't fit is that fifth y. So that extra y is going to have to stay off to the side. So these are all perfect squares, and this is not a perfect square. Since it's a square root, I can pull perfect squares out. So what's going to happen is when I pull this out, I'm going to get a 7, because I'm going to get the square root of 49. I'm going to get an absolute value of x, because I know that I'm pulling out an x, right, because it's the square root of x squared, right? But I don't know if x is positive or negative because it's a variable, right? It varies. So I have to say that it's got to be positive, right? I'm also going to get an absolute value of y squared, which we're going to talk about why I don't need that in a sec. So I won't need this absolute value, and we'll talk about that in a sec. And I'm going to get an absolute value of z to the third, and then the guy that's stuck in there is the y. The reason I don't need the absolute value around the y squared is because y squared can't be negative, right? So y squared is greater than or equal to 0 by definition because I'm squaring whatever's in there. So what's going to happen is I'm going to put the stuff out here that doesn't need the absolute value, and then in the absolute value, I'm going to put an x and a z cubed, right? So that's the stuff that needs the absolute value, and then I have a square root of y. So there's my fully simplified answer. And the reason I need the absolute value is because I don't know the sign on x, y, and z. Now, with cube roots, I don't have to worry about that, right? So when I deal with a cube root, what I'm going to do is I'm going to split things into perfect cubes and not perfect cubes. Well, -27 is a perfect cube. An x to the sixth, because 6 is a multiple of 3, is a perfect cube, but that leftover x isn't, right? A y to the third is a perfect cube, and the z squared is not. So what I've basically done is I've split this into things that are perfect cubes and things that are not. So when I do that, out of my perfect cube, the cube root of a -27 is a -3. The cube root of an x to the sixth is going to be an x squared, because x squared times x squared times x squared would give you an x to the sixth. And the cube root of a y to the third is going to give me y. What's left in the cube root is an x and a z squared, because they couldn't make it out of the cube root. Notice I don't need any absolute values because odd roots don't require a positive output, or a non-negative output, I should say. All right, go ahead and give P1 a try. You're going to fully simplify the expression. Again, I would suggest that you split this into stuff that's a perfect square and stuff that's not. So if I split this into two sections, right, stuff that's a perfect square, 64 is 8 squared. A to the fourth is a squared squared. B is not a perfect square. right? C squared is, but that leftover C isn't. So these are all perfect squares. These are very much not, right? And I have more root than I need. All right, cool. So what I'm going to do now is I'm essentially going to, and I didn't do this step in the last one, but if it helps you, can actually split them apart into two separate roots, right? So you can make this a root, which we can simplify, and this the other root. So this thing's kind of stuck. You can't do anything about them because they don't make their way out of the root. But I can simplify this. The square root of 64 is an 8. The square root of a to the 4th is an a squared, which should go in an absolute value normally, but isn't going to need it because it's a squared. The square root of a c squared is going to be a c. It needs to be in an absolute value. So what's going to end up happening, sorry, don't want an equal there yet. I forgot my root, right? So I still need my radical with my bc. So I don't need this because a squared can't come out negative, right? So I'm going to rewrite this as an 8a squared because that all has to be positive. But I don't know what c is, so I need an absolute value around c and then the square root of bc. When we go to do a fifth root, remember odd roots are easy. We don't have to worry about things like perfect, like absolute values because of negative answers. But I do need to worry about things that are perfect fifths, right? So I'm going to split this essentially into two pieces, right? Things that are a perfect fifth. 32 is a negative 2 to the fifth. F to the fifth would be a perfect fifth, but that leaves an F by itself. G to the fifth is a perfect fifth, but that, and then I have this H squared, right? So what's going to happen is these are perfect fifths and these are not, right? So I can, if it helps, you can split this into two radicals. Oh, sorry, that's not a square root, that's fifth root, my bad. I forgot the index. So a negative 32 f to the fifth, g to the fifth, times the root of stuff that's not going to make it out of the root, right? So it's a fifth root of that stuff. So what's going to happen is I take the fifth root of negative 32 and get negative 2. Fifth root of f to the fifth is f, fifth root of g to the fifth is g, and then I'm stuck with this fifth root of fh squared. Again, no need for absolute values because it's an odd root. All right, moving on. So I kind of already cheated and showed you this one a little bit, right? So the product, if you have a product of two things inside a root, you can split them apart into two roots, and I was actually sort of secretly already doing that. And if you have a quotient of something inside of a root, you can split it into a quotient of the two roots, right? So like two roots with a quotient. Again, notice the caveat that b cannot be 0 because you're not allowed to divide by 0. Also, as a reminder, we learned way back when that we can write fractional roots fractional exponents as roots and vice versa, right? So the nth root of x to the m is the same as x to the m over n, right? So let's go ahead and walk through this. All right, so we're going to clean this up a little bit, right? So there's a few different ways to do this. I'm going to suggest that a really good option is to combine the roots first. So I'm going to start by rewriting this fractional root as a cube root. So this is actually the cube root of a 27a b cubed times the cube root of a 5a to the 4th b. Now I'm going to suggest that the best option is to put everything inside one root together first, because sometimes something's going to simplify more than you expected. So I'm going to recognize right away that it doesn't behoove me in any way to multiply the 27 times the 5, because 27 is a perfect cube and 5 is very much not. But it might benefit me to combine some of the a's and b's together. So I'm going to get that this is an a to the 5th and a b to the 4th, right? So that's all combined into one root. And then I'm going to do that same thing I've been doing, where I split stuff into what's a perfect cube and what's not. So my perfect cubes are 27 a to the 3rd, right, which means that not in the perfect cube category, I have a 5 and an a squared, right? And a b to the 3rd, which means that I have a solo b that's stuck over there. So these are perfect cubes, and these are not, right? So if you want to split them apart into two roots, you absolutely can, right? If you don't need this step, that's also fine too. So 27a cubed b cubed times the stuff that's just going to stay a root because there's nothing I can do about it, the cube root of a 5a squared b, right? So when I simplify the stuff that's perfect cubes, the cube root of 27 is a 3, the cube root of a cubed is an a, and the cube root of b cubed is a b, and then I'm stuck with the cube root of stuff that I could not simplify. And that's the best I can get, right? There's no need for any absolute values because they're odd roots. All right, let's go ahead and walk through b. So again, for b, I'm going to suggest that your best option is to clean up the roots a little bit first. So I have an 8 over a 4, which I can clean up whenever I want, and inside here I have a 54x to the 5th over, inside this root there is a 3x to the 3rd. So I'm going to suggest that it benefits you to first cancel the 8 and 4 to just get a 2, and then make this one big root. So a 54 x to the 5th over the 3x to the 3rd. I'm going to clean that up a little bit. I have a 2. Make sure you notice that's not the index, right? That's a 2. It's a 2 over 1 if it helps you, but it's not inside the root. It's not the index. It's a number in front. So 54 over 3 is going to give me an 18 and an x squared. Well, suddenly it's a lot easier to pick out the stuff that's perfect squares, right? So I have this 2 in front of, I think I have a 9x squared. Those are all perfect squares. And then a 2 that's stuck inside the root. So if you need this step, you can split it into the square root of 9x squared times the square root of 2, right? If you don't, it's fine to skip that step. So I'm going to get that this ends up being a 2 times a 3, because that's what the square root of 9 would be, times an absolute value of x, and then a root 2. The last thing you'd need to simplify this is to make it a 6 times this absolute value of x times a root 2. And it doesn't really matter what order you put this in. If you wanted to put the absolute value at the end, you totally could, right? You could do something like this. It doesn't really matter. It just needs to be clear that the only thing in the root is the 2. All right. Go ahead and give this one a try. It's the same concept as what we saw in E2. So I'm going to suggest that you start by rewriting. So I would you might even just want to cheat and say, oh, look, hey, that's a cube root, right? That might make your life a lot easier. When you put everything inside the cube, you're going to end up with the 3 times the 9. So 3 times 9. You're going to have an r to the 2nd and an r to the 3rd, and you're going to have an s to the 3rd and an s to the 4th. So I'm going to clean that up first. And I'm going to get a nice happy 27, which is awesome because I have a cube root. I'm going to get an r. So I see that I have an r to the 5th, right? You can start it with an r to the 5th, and we'll clean it up in a sec, and I see I have an s to the 7th. So when I clean this up into perfect cubes and not perfect cubes, 27 is a perfect cube, and any r with a power that is a multiple of 3 will also be a perfect cube. So the r cubed is a perfect cube, but the squared needs to be somewhere else. And the s to the 6th would be a perfect cube, but that last s needs to stay off by itself. So these are perfect cubes, and these are not. If you need the step where you write them as 2 separate roots, that's fine. If you don't, you can just go ahead and, so if you need this step, if you need 27 and r cubed and s to the 6th, all of which will simplify, and you need it times the root that's not going to simplify, that's totally fine. If you don't need that, it's also okay to just jump to this being a 3 and an r and an s squared in front of this cube root that wouldn't simplify. Again, because it's an odd root, I don't need to worry about anything like absolute values. All right, so let's do one final part to this problem, right? So I'm going to suggest that, again, if you want, you can just cheat and say, hey, look, there's a square root, right? So I'm going to make this a square root of a 54x cubed y cubed over a 3x y squared. So when I cancel the 54 and the 3, I'm going to get an 18. When I cancel the x cubed over the x, I'll get an x squared. And when I cancel the y cubed over the y squared, I get a y. So now when I split this into perfect squares and not perfect squares, 9 and x squared are perfect squares. 2 and the y are not, right? So this is a perfect square. This is not. So if you need this extra step where you split it into the 2 roots, that's totally fine. If you don't need that, that's also fine. So this is going to be a 3 and an absolute value of x, and then this is a root 2y. Needs to be in the absolute value because, again, I don't know if x is positive or negative, and the thing that comes out of an even root has to be non-negative. All right, and that's it for that video.